Galaxies that form and evolve in the same environment will have their shapes and positions heavily correlated. This is because the shapes and as the galaxies form, the potential in which they are created torques and pushes them, shaping the galaxies in similar ways. Now, these intrinsic alignments are often seen as a nuisance in studies of cosmic shear. This is because cosmic shear relies on the assumption that galaxies, if you average the shapes of many galaxies, the intrinsic ellipses average out to zero, and you're left with the shear, just the shear caused by the dark matter or the distribution of matter. However, as if these galaxies form in similar environments and therefore have correlated shapes and positions, this assumption no longer is valid. So therefore, modeling the intrinsic alignment of galaxies is incredibly important, because you have to understand exactly how this impacts the overall correlation function of shapes in your universe, and thus not be biased when you make your inference on the cosmological parameters. However, although this has been predominantly seen as a nuisance, perhaps there's more to it, because the intrinsic alignment of galaxies are sourced by the local environment, and that environment is predominantly dark matter. So if you change the distribution of dark matter, you'll also change the intrinsic alignment of galaxies. The distribution of dark matter is heavily dependent on the fundamental properties of dark matter. So therefore, if you change the fundamental properties of dark matter, this will imprint on the intrinsic alignments of galaxies. So therefore, perhaps it's not just a nuisance parameter, and we can actually use the intrinsic alignments to understand dark matter itself. And this is what my talk is going to be about today. I'm going to talk about how the self-interactions of dark matter can imprint on the intrinsic alignments of galaxies. This work has been in heavy collaboration with Elisa Cesari at Euclid University, and also Andrew Robertson and Ian McCarthy. Now, the cold and collisions dark matter paradigm has been incredibly successful in explaining the large-scale distribution of matter. Here I'm showing a recent press release from the Dark Energy Survey, and you can see the full sky with the Milky Way band going through it, and the largest dark matter map that's been created in the center. This dark matter map has been created from gravitational lensing, and if you compare this to what a simulation is of just a simple cold and collisions dark matter particle with nothing else from the Millennium simulation, you see the similarities are uncanny. And in fact, that the web-like texture is persistent between both. So you can see that just with a very simple dark matter model, cold and collisionless, you can reproduce the large-scale distribution of what we observe incredibly well. The problem we have, though, is this doesn't tell us anything about what dark matter actually is. In fact, this just tells us that this very simple particle works, but not the mass, not its interactions with other particles, not nothing. Not only this, if you actually look very closely in the very small scales of these predictions, they potentially and seemingly break down. So is there some way that we can look closer at the smaller scales to understand whether or not this model is successful, and as such, can we get an idea of what maybe, is there something that's telling us in the small scales of dark matter? In particular, the self-interaction cross-section has been of interest in the last decade as some solutions to some of the potential discrepancies that are observed in the small scales of distributions of galaxies between simulations and observations. Here I'm showing a very simple plot of the strength of the cross-section against the velocity of particle interactions. So, for example, in dwarf galaxies, the particles move about 10 kilometers a second, so their particle interactions are about that. In galaxies, they move about 100 kilometers a second, and therefore you've got that's about around the center of the center. And in cluster galaxies, the particles are moving about 1,000 kilometers a second. Now, what I'm going to show is the observations and the constraints on the self-interactions to date. And what I'm showing here is the three different areas I just spoke about. So in the very left-hand side, we see Milky Way satellite galaxies. And this is coming from the fact that galaxies seem to have, the Milky Way satellite galaxies seem to have an anti-correlation between their pericenter and the density of dark matter in the center of the galaxy, which can potentially only be explained from self-interaction dark matter. Should this be the case, and should this be explained by self-interacting matter, you'd require a cross-section of about 100 centimeters squared per gram to reconcile the observations with the simulations. So you can see this very high here. Now, if we go to the clusters of galaxies, the constraints are much further down, around the 1 to 0.1 centimeters squared per gram level. So you can see that they are in tension with one another. However, what I show in the white line is a very simple model of self-interactions that we see every day in our real world, which is a velocity-dependent cross-section. So, for example, proton-proton scattering is a velocity-dependent cross-section. The slower they move, the higher the cross-section relative to one another. So if you plot such a similar scattering process here, you see you get this 10 to the minus 4, velocity to the power minus 4 as you go off, and then you get a velocity independent at low velocities. Sorry, yeah, you get velocity independent cross-section at low velocities. And you can see this explains the data incredibly well, which is quite tantalizing. However, we need to get more constraints if we are to understand these observations better, and whether or not the Milky Way satellites are telling us something quite extraordinary. So what we can do is we can go to the what I did was with Elisa and Ian and Andrew is we asked the question of whether or not we can constrain self-interactions using the intrinsic alignment of galaxies. So the first thing we did is we went to the Bahamas suite of simulations, and we ran 4 different cross sections of dark matter to five different dark matter models, and we just looked at the shapes of galaxies. Now, these simulations include all the standard baryonic feedback processes like AGN and supernova. What we did is we looked at the 2D eccentricity and the 3-dimensional axis ratios, the medium over the major and the minor over the major. And in each color, I'm showing a different dark matter model. So in white, you have the collisionless dark matter, and then you have increasing cross sections in yellow, pink, cyan, and then you have a velocity-dependent cross-section in blue. And the key finding from this is we found that the self-interactions make the galaxies more round. Now, in this situation, we've only selected the central galaxies in halos. This is the most massive galaxies in the simulation, in order to ensure we have enough particles to make the measurement of the shape. So you see that the central galaxies become more round as you increase the cross-section. So this is clearly going to change immediately the intrinsic alignment of galaxies if one part of the correlation between the galaxy shapes and the position of galaxies is altered. The next thing we looked at was just the clustering of galaxies. So whether the positions of galaxies would alter and be changed. Here I'm showing in the top part of the plot, we're showing the absolute clustering, but cross-correlation between the central galaxies and all the galaxies in the simulation. And in the bottom, we'll show relative to the CDM as a function of the co-moving distance in megaparsecs per inch. And you see here that the self-interactions are suppressing the cross-correlation between central galaxies and all galaxies in a roughly scale-independent way. So you can see that not only are the shapes altered, but the positions are also altered by the self-interactions of dark matter. Now, what happens if we correlate the shapes of the centrals with the positions of all the galaxies? So here now, I'm showing in the top, I'm showing the alignment of galaxies and the cross alignment. So you expect the galaxies to align perpendicular because of the tidal forces, but then you'd also there's also the 45-degree offset, similar to the the cross shear in cosmic shear studies that are sanity check. And then the bottom I'm showing with respect to CDM again. And this is what we find. So in the top, in the dotted, we've got this cross shear, which we expect to be 0, which is a good null test, so we find is completely consistent with 0. And then we can see the 5 different dark matter models. In the white, we have the collisionless dark matter, and we see the increasing cross-section suppresses the intrinsic alignment signal. And we can see more clearly in the bottom panel, where it's relative to CDM, not only is this suppressed, but it's expressed in a scale-dependent way, such that at large radii, it tends back to what we'd expect from CDM. Now, one of the big questions would be how sure these are different from AGN. and the baryonic feedback processes that occur during the simulation. And this is a valid question. So what we did is, in order to understand what the size of the uncertainty is in the AGN feedback, is we simulated two more feedback scenarios in the simulations that represented the extremes of what was consistent with data. And what we found was this. So here in the gray region is the variance in the two dark matter models from, sorry, not the matter model, the two AGN models. And then again, I'm showing the four dark matter models with positive finite cross sections. And the first thing you'll notice is that at the small scales, even at 0.1 centimeters per gram, you are outside the regime of the most extreme AGN feedback. Not only that, is that the AGN feedback is somewhat velocity independent. So therefore, you shift the whole correlation function down. However, the self-interactions are much more scale dependent, and you'd expect them to tend back towards CDM at large radii. So this could potentially provide a discriminacy signal between whether it's AGN feedback or whether it's self-interaction dark matter. Now, in a more practical sense, how we would measure this in real life, we wouldn't just directly compare potentially the profiles, but we can model them and then try and understand the parameters of that model. So, for example, we did a very, very simple model here, which was just modeling the correlation functions, the shape position correlation functions as a power law with a amplitude A and an index beta for different dark matter models. And what we found was this. So we found first, what was expected is that the amplitude of the power law is extremely dependent on the cross section. And we know this because we saw it suppressed dramatically. However, what will be interesting is whether or not there's a scale dependency, whether the index is changing as a function of cross section. And this is what we find. We find indeed that the index of the power law is also changing as you change the cross section. So therefore, this is really interesting because if you have a shape measurement method where it's hard to constrain in between your theory and your observations, the amplitude, but you can constrain the beta very well, the shape of the power law very well, you can use that to constrain the self-interaction cross section, which will be independent yet of the shape measurement method. So that's very exciting. The other exciting thing is that if you can try and measure the intrinsic alignment signal for different parts of the galaxy themselves, the shapes of galaxies, you also get different signals. So what we did, we looked at the shape position correlation functions for if you measure the galaxy at 30 kiloparsecs, and if you measure the galaxy at 100 kiloparsecs. Now, what I'm showing here is the amplitude again as a function of cross section for the two different shape measurement methods. And what we find is they have two different dependencies on the cross section. So you can measure the two and measure the ratio, for example, and understand there where that aligns with what you'd expect, and whether that's consistent with collisionless dark matter or self-interacting dark matter. So you can see that there's many avenues you can go down to understand whether the imprint of self-interactions on the intrinsic alignments is real. Now, there's also imprints due to mass and redshift change. However, I haven't had time to show you today, but this is also a possibility. So to summarize, the self-interactions alter the distribution of dark matter, which in self imprints on the intrinsic alignments of galaxies. With forthcoming studies and forthcoming telescopes that will measure and constrain the self-interaction the intrinsic alignment signal incredibly well for cosmic shear studies, we'll be able to use that intrinsic alignment signal to be able to constrain the self-interaction dark matter, which is incredibly interesting. However, obviously, there's clearly much more we need to do. We need to model these in an observed way to understand how these would be observed and potentially with larger simulations. And I thank you very much.